So hello student, welcome back to the physics lecture. So today we will be talking about a new topic in this chapter, mechanical properties of fluid. Okay, and that is known as principle of continuity. So principle of continuity says that here the definition is written for principle of continuity, and it says that when an incompressible and non-viscous liquid flows in a streamlined motion through a tube of non-uniform cross-sectional, then the product of area of cross-section and velocity of flow at every point in the tube remains the same. Okay, so that means I want to just picturize here for principle of continuity, and here you can see that the area of cross-section of tube varies. Okay, here is the area of cross section is something big, and at the other end you can see that the area of cross section becomes small. So in this we have to prove that in a streamlined flow, okay, in a streamlined motion of the liquid, we can analyze that the liquid is flowing in the form of layers that we have studied in case of streamline. Okay, like this, and this flow is also known as laminar flow. Okay, so here is the direction of the flow of the liquid, and here you can see that the liquid is entering at this phase. Let this phase be of area A1, and let the other phase from where it is going out, it will be A2. Okay, so here we have to show that here while entering it may be having some different velocity, and at the other point where the area of cross section A2 lies, at that point there will be some different velocity. Okay, so let here the velocity be V1 and here the velocity be V2. That we have studied in case of streamline also, that the velocity varies. Okay, if I consider two different points on the same line, on the same streamline, if I suppose. Okay. So in this, if I consider this x point, okay, or the area of cross section which is x, or let us say that it is A1. So what is the amount of the liquid which is entering in 1 second? Okay, so what is the amount? That means how much mass is entering in 1 second. So to calculate the mass which is entering in 1 second, it is very important for us to calculate first that how much is the volume which is entering in 1 second through this surface area, that is equal to A1. Okay, so the volume we have to prove. This is our proof, and what we have to prove? To prove for such condition, we have to prove that A1 into V1, okay, is equals to A2 into V2. This we have to prove, and this will be valid for the, even if I consider this A1 one cross section to be at this point, then another cross section can be evaluated, it can be considered to be in between also. Okay, so the velocity at that cross section area will be something else. So this equation, for if suppose that I am talking for these two cross sectional area which is having the velocity of V1 and V2, okay, about the flow of the liquid, I have to prove that this product of the area of cross section and the velocity through that area is equals to another area of the cross section, and the velocity of the liquid which is passing through that area of cross section is what? Is same. Okay, this we have to prove in this equation of continuity. Okay, so if I suppose that here is another cross section area, and for these two areas let us assume that we have to satisfy the equation of continuity, then this equation, this format of the equation is valid for these two areas also. Okay, so for here there will be some different velocity, and for this there will be some different area. Okay, so the product of A1 into V1 will be equal to A to V according to this figure. So let us try to first see that how much volume is entering through cross sectional area A. Okay, so liquid enters the cross sectional area A, has the velocity of V1. So in 1 second, how much is the volume which it is covering? Okay, so the volume volume covered in 1 second, in 1 second through A1. How much it will be? Okay, so for 1 second, how much the distance it will cover? Distance is equal to speed into time, and distance will be equal to v1 into t, that will be 1 second. So the distance will be, for 1 second it will be v1, because v1 into 1 will be v1 only. So volume is what? Distance into area is the volume. Okay, so distance into area is the volume. So let at 1 second also, after 1 second also, let us assume that the speed that the liquid is passing through the same cross sectional area. Okay, let there be no variation in the area after 1 second also. So in that case we can write that volume is what? Area into length, the length which the liquid is covering. So in that case the length we know that is how much? v1 for 1 second. Okay, because distance is what? Speed into time, and time is 1. So it will be v1 only, and into the area, that is equals to a1. So this is the volume which is what? This much of the volume is covered in 1 second, or this much volume water or the fluid entered in 1 second. Okay, covered कह सकते हैं या entered कह सकते हैं. Similarly, for another, we can also say that the volume which will be taken out through that area in 1 second will be equal to how much? v2 into a2, in the same way. But before going through that, let us calculate that how much is the mass of this much of volume. Okay, how much is the mass of this much of volume? So the amount of the liquid which is passing in 1 second is having how much mass. So if I consider that the liquid which is flowing has a density of rho, so we know that density into volume is what? Density into volume is mass only. So the mass entered in 1 second will be equal to rho into v1 into a1. Okay, so let this be equation number 2. And now come back to that cross sectional area, that is the second cross sectional area, and for that similarly we will be writing what? The mass of the liquid coming out. Okay, how much is the mass of the liquid which is coming out through this cross sectional area? Okay, so similarly we can write that mass of the liquid not entered, now that has to go out. Okay, coming out in 1 second, that will be equal to rho, the rho will be same, and v2 into, according to the same format. Okay, so now what we have to do? So we know that how much the liquid will enter, that much amount of the liquid has to leave. Okay, because in this case what we have to show that the flow is what? Streamlined. So according to that concept we have to consider that the amount of the liquid which is entering through one end must leave the other end also. Okay, so in that we can consider that the masses which are coming in for 1 second will be equal to the mass of the fluid which will be going out in 1 second. Okay, so this is our consideration. So from here, if I name this equation number 2, so I can equate these equations. Okay, so if I equate these two equations, then we will be getting what? A1 into V1 is equals to A2 into V2, like this. Or in case of dot, in terms of dot product, also we can write A1 V1 is equals to A2 V2. That's what we can write. Okay, so this is our equation of continuity. That is A1 V1 is equals to A2 V2. And whatever cross sectional area we consider in between also in this entire non-uniform tube, we can apply this equation of continuity, that is valid. Okay, just we have to know the velocity through that cross sectional area, that is very important. And this formula which I have bracketed here is also important. Okay, so what is our final conclusion from here? From here you can conclude that to hold this equality, it is very important that from here you can see that the area A1 is greater than A2. Okay, so that means this quantity is greater than this quantity A2. hold this equality, what has to be here? V2 should be greater than that of the V1. If A1 is greater than A2, to hold this equality, we have to conclude at any cost that V2 has to be more than that of V2. Yani if A1 is greater than A2, so what we have to conclude? We have to conclude that in this case V2 will be greater than V1 at any cost. Okay, this will be our consideration. So this is very important. So from here what we can conclude in theoretical manner, the velocity of the liquid is smaller in the wider part, okay, of the tube and larger in the narrower parts of the tube. So according to this area of cross section, we can conclude that what will be the magnitude of velocity. Okay. Now let's talk about Bernoulli's theorem. Okay. So Bernoulli's theorem states that when an incompressible and non-viscous liquid flows in a streamline. Okay, here should be the liquid term. Liquid flows in a streamline motion from one place to another, then at every point on its path the total energy per unit volume is constant. Okay, that means the viscous the liquid is what? It is incompressible, that cannot be compressed easily, and non-viscous, that means the force of attraction in between the adjacent layers of the liquid which is flowing is what? Is supposed to be negligible. Okay, and the flow is a streamline, as you can see, like this. It is a streamline. It is a form of curve like that. Okay, so it is very important first of all that what is total energy per unit volume, which is written here. Total energy comprises of pressure energy, kinetic energy, and potential energy. And this is the energy per unit volume. This is P, which is written here. It is pressure energy per unit volume. It is what? Kinetic energy per unit volume, and this is potential energy per unit volume. So first of all, before deriving this equation, let us try to understand that from where this pressure energy comes out. Okay, from where I can write that this is P only. From where I can write that kinetic energy per unit volume is this much. From where I can write that potential energy per unit volume is this much. Okay, so for pressure energy, this is not a part of this derivation, but to understand this, to prove this, it is very important first of all to just know the mathematical formula of each and every energy per unit volume. Okay, so pressure energy is equals to what? Pressure is what? Pressure energy is that energy which is what? Equal to the work done. This pressure energy is equals to the work done, as we have seen in many cases when we are studying our mechanical system also, that sometimes we do the work and that work is stored in the form of energy. Okay, here also what happens? Here I consider that this is the area of the tube. Okay, here is one area of the tube and it is what? It is having the cross section A. Okay, and here there is what? If I am applying P amount of the pressure, then the liquid which is there, suppose that there is a liquid column. Okay, it will be displaced by L. Okay, this liquid at this part will be displaced by L, let us say. Okay, if I am applying P pressure, because there will be the force on this area and that will displace the liquid column further. Okay, so pressure energy is equals to the work done, that is done. Okay, and that work done will be equal to the force into displacement, and displacement you can see in the column is L. It is denoted by small s. So force is what? Force is what? We can write in terms of pressure. Okay, because pressure is force upon area, and force is equals to pressure into area into length. This is what we can write. Okay, so this is what? This is the pressure energy. But here what we have to find? The energy, total energy per unit volume. That means for this pressure energy we have to divide it with volume to get what? Pressure energy per unit volume. That will be equal to P into A, that is our pressure energy, divided by volume, that will be equal to A into L. We know. Okay, area into length is what? Volume. This much of the area has been displaced by L so this will be the amount of the volume. Okay, so from here this will cancel and the remaining will be P. That is this expression we got. Okay, now further let's see that what is kinetic energy per unit volume. So we know that kinetic energy is what? Kinetic energy for mass m moving with velocity v is denoted by kinetic energy per unit volume can be written like half of m into v square. Okay, there is mass m of the liquid which is moving with v velocity. Okay, over the volume v, let us say it has been moved. Okay, so it will be divided by v according to this kinetic energy per unit volume. So mass upon volume is what? Density. So we will be getting half into rho into v square. This is the second expression that we got. Okay, this is the second expression that we got. Is it clear? So let me adjust the camera so you can see like this. Okay, so now let's talk about potential energy per unit volume, that is this term, from where this term has come. Okay, so we know that, let me erase. So we know that potential energy for a mass m which is at h height, we denote it by mg into h. Okay, and this when divided by per unit volume, if I talk, then I can write it by dividing it by v. Okay, if v is the volume of that liquid which is at h height and n is the mass of that liquid. Okay, so this will get reduced to rho into g into h because mass upon volume is what? Density. So from here we got these equations. Okay, from these terms. Okay, the mathematical description of these terms we got. Now let's concentrate ourselves on deriving this equation, that how we can say that the total energy which is there per unit volume is constant for entire point inside the tube. If I am talking about this point, if I am talking about this point, if I am talking about this point on the straight line, then we have to say that the total energy per unit volume will be same at every point. Okay, so let's see the proof. Okay, let me erase the entire thing to prove. So now let's talk about the proof of Bernoulli's theorem. Okay, proof. That is P plus half into rho into v square plus rho into g into h equals to constant. Okay, let this be the required figure that we are having. This is the ground. This is at h1 height as I have drawn, and this is at h2 height. Okay, this is the cross-sectional area. Let us say that this is A1 and this cross-sectional area be A2. Okay, so externally, from external environment, what will be having? There will be some pressure. Okay, from here it will be having some V1 velocity. Okay, and if I suppose that this is a streamline manner, it's flowing in a streamline manner, so here it will be coming out to P2 velocity. Okay, so now this is the area A1, this is the density of the liquid which is flowing as rho, that we have decided earlier also. Now let here be pressure P1 which is acting on the liquid to flow, and from here let the pressure P2 be acting, okay, to oppose this flow. Now what is the work done? What is the work done by the liquid which is flowing through this end? Okay, in 1 second. Okay, so for 1 second, how much will be the distance that will be covered by the liquid? If the liquid enters through this end, so it will be equal to how much? It will be equal to V1. So work done will be how much? Work done at A1 will be how much? It will be equal to force into displacement. And let the displacement be how much? Work done at A1 in 1 second. In 1 second. This will be displacement. Okay, because displacement is what? Speed into time, and time is 1. So it will be equal to the speed only at this cross-sectional area. So force will be, there will be some force corresponding to the pressure. How much will be the force? It will be P1 into A1 into V1. This is what we can write. Okay, so this is work done at A. Okay, what will be the work done at the other end? Okay, similarly we can write down that work done by the pressure. This is by the pressure P1. Okay, by P1. Okay, here the work done at A2 will be by P2, and that will be equal to P2 into A2 into V2, corresponding to all the terms which we have. Okay, so what will be the net work done in this case? Net work done will be how much? P1 into A1. I am writing in terms of dot product. Okay, minus, or one can say that it will be equal to P1 into V1 into P1 into A1 into V1 minus of P2 into A2 into V2. This is what we can write. This is the net work. Is it clear? So this work done is what? This work done will be stored in the form of the energy. Okay. So let's try to see that what is the amount of the energy which is coming. Okay. What is the amount of the energy which is at this end, and what is the amount of the energy which is at this end. So if I am talking about the total energy, then that will be what? That will be according to the mechanical system that we have studied, that is the sum of kinetic energy and potential energy. Okay, so how much there is the increase in the kinetic energy? Okay, you can see that here the cross-sectional area is wide. A1 is greater than A2. So correspondingly, according to the principle of continuity, we can say that V2 has to be greater than that of the V1, because the area of cross-section is less. Okay, this we have studied in the principle of continuity. So what will be the increase in the kinetic energy? Delta K will be what? Increase in the kinetic energy will be half of m of V2 ka square minus half of m of V1 ka square. I am talking for 1 second, and the masses will be same. The mass that will be dispersed and the mass that will be entering will be same for that liquid. Okay, for 1 second I am talking. So how much it will come? It will come half into m, that will be same. Okay, for 1 second same mass is entering and same mass is dispersing. So I have taken common V1 ka square minus V2 ka square. And what about the potential energy term? Potential energy term will decrease, you can see, if I am talking about fluid. Here the height is more, here the height is less. Okay, so the decrement in the potential energy will be there. I have shown it by downward arrow. M into G into H2, H1 minus H2. Okay, so here you can see that the kinetic energy is here the kinetic energy will in this case what will happen? In this case, sorry, I have written opposite. The kinetic energy will increase, okay, and potential energy will decrease like this. So the total energy will be how much? It will be the sum of kinetic energy plus potential energy. That means the net work done which is here will be equal to the sum of these two. Okay, so from here we can write that work done will be equal to stored in the form of total energy. Total energy. Okay, the work done, the net work done which we have calculated, that will be equal to the total energy term that we are having. Okay, so since you can see that here there is a decrease in the potential energy, so this much is the magnitude, that by this much magnitude it will decrease. So if I talk about the total energy, so it will be equal to half of m of V2 square minus V1 square minus of, now we will not writing plus. Okay, we will be writing this quantity with negative, and that will be equal to m into G into H1 minus H2. What we can write. That's why I am using this negative sign. And now we have to place it here. Okay, we have to place it here. So how much the value will come? So further we can see that according to equation of continuity, we can just modulate this equation further. Okay, let me erase this and let me explain it. So according to equation of continuity, we have A1 V1 equal to A2 V2, and that will be equal to how much? M upon rho. This is what we can write. Okay, A into V for 1 second. Okay, for 1 second. This is distance into this area. V1 will be the distance for 1 second, and this will be A into length. A into length. So that means this is what? This is the volume, and we know that volume is what? Mass upon density. This is the mass which is entering for 1 second, and this is the density. So just replace this. So from here we get what? P1 minus P2 m upon rho. This is what we get. Okay, this is what we get from here. Now from these two equations we put here that work done which we are doing to show the total energy term, that in total energy we have to place this value and the work done which we got in terms of this pressure difference and mass and density. So just place this formula and let's see that how much it is coming. So while placing, what we get? P1 minus P2 m upon rho is equals to half of m of V2 square minus V1 square minus m g h1 minus h2. Okay, so from here you can see that the mass term will cancel out. Okay, and P1 minus P2 will be equal to rho will be multiplied here. So it will give this will equal to half of rho into V2 square minus half of rho into V1 square and minus rho mg h. Sorry, this mass will also cancel out. Okay, so rho into g into h1 minus plus rho into g into h2. This is what we get. Okay, so just put the term which is containing 1 in the suffix on one side and just put the term which is containing 2 on the other side. So from here what we got? From here we got this equation, that is P1 plus half of rho into V1 square plus rho into g into h1 is equals to P2 plus half of rho into V2 square plus rho into g into h2. Thus you can see for two different cross-sectional area at two ends, we have proven that this is coming in this format. Okay, that is, this stands for the pressure energy per unit volume at first end, kinetic energy per unit volume at first end, and potential energy per unit volume at first end. Similarly for the second end also, the same format is coming. P2 P half rho into V2 square, half rho into V, and half rho into H2. This. So we can prove from here that we have proven, and we can write the general term that half into rho into V square plus rho into G into H is always constant for entire point which is there inside the flowing liquid, of the tube. So whether I take this area to be here, whether I take this area to be here, or very close to this, we should know that what is the value of the velocity. We should know that what is the value of that height. Okay, so we can calculate that what is the total energy at that point, and this is the proof of Bernoulli's theorem. Okay. So by dividing by different parameters, you can get the pressure head. Okay, you can get the velocity head and gravitational head also. Okay, so this is the main formula of Bernoulli's theorem, and we know that by applying what are the conditions that we can picturize, and according to the concept that we know, how we derive this Bernoulli's equation. Okay, so this formula is important for us.